Alright, hello everybody, this is Ice, and welcome back to another episode of the Redstone Calculator tutorial series. In this video, we're going to start on the mathy part of the calculator, but before we do that, we just need to do one quick thing. In particular, to solve a problem that we left unsolved in episode 7. So what do we have right now? If we go over here and we enter some number, 555 in a moment, then say we want to make it want to make it negative. Like that. And then we go to reset. The number disappears, the minus sign doesn't. And we want the minus sign to disappear, so we're going to need to fix that. Now, it's not the most beautiful fix I've ever come up with, but it does need to be done because we do want to be able to reset our minus signs. So, to do this, what we're going to actually have to end up doing is inverting these minus signs. So, what you want to do is you want to come out here and get rid of these blocks that make up the minus signs, and move them in one. Now, you might be asking why we do such a thing, but you will see. So now we have nothing there. Then we come over here, grab the other ones, which should be right here, and once again move them up. Just like that, and get rid of that. Okay. Now I guess I'll go around the back here, all the way around the back. And now, let's see what we can do with this. First thing you want to do is you want to make these wires compatible. Not too hard, just like this. Like so. And like so. And then what you want to do is hook up your reset wire. Now your reset wire will run directly next to this screen like this. So you'll put a block here and have it coming up like so. And basically what we want to happen is we want this wire to go into both of these, and when it sends a long pulse, it will cause these pistons to push out their blocks and reset this thing perfectly normally. So you'll see how that works in a moment. To do this, we're just going to stick repeaters underneath here so we don't have to come around, and connect this up. Nothing too fancy, but it's just a quick fix that is definitely necessary. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, block, repeater, repeater. Okay, so there's that. For the rest of this episode and the ones that follow it, I'm going to be going through a brief overview of how we do binary arithmetic. Now, you might be saying that's a bit of a basic concept to be doing in the calculator tutorial, but I figured that this series should be aimed at anybody who knows a little bit about binary counting, for instance, and therefore I should be completely comprehensive, starting from the beginning with addition and moving up to more complicated things. Now, for those of you who are watching this series and already know about binary addition and what 2's complement is, then you can feel free to skip these next 2 videos because they're going to be very basic. But I think it's important to have some idea of adders right here. So that's the plan for the next 2 episodes, hopefully. Hopefully it doesn't have to go to 3. Alright, so without further ado, I think we should get on to the topic of binary addition. Again, if you already know what this is, then skip this episode, by all means. But I just want to cover it myself, so that we're all good, and all on the same page. So, for binary addition, first of all, let's do a binary addition problem without adders or whatever. So, let's do, for instance, let's do 5, so that's 1, 0, 1, like that. Does that look right? Yep. Plus, say, 2. 0, oops, just like that. I think that's how I'm doing it here, like that, and like this. So this should be 5 plus 2, like that. So how would we do a problem like this? Well, binary addition works a lot like regular decimal addition. We know this is 5, because this is a 4-bit, this is a 2-bit, but it doesn't count because it's 0, and this is a 1-bit, and 4 plus 1 is 5. We know this is 2 because we only have the 2-bit on. So how do we add these 2 binary numbers? We do it in the exact same way as we add normal numbers. So for instance, if we come over here, we add up 1 plus 0. We can do that, can't we? It is just 1. Good. Go over here, we add up 0 plus 1. Hey, look, that's 1, 2. 1, not 1, 2, but 1 as well. And finally, 1 plus 0 is again 1. So we get that 1, 0, 1 plus 0, 1, 0 is 1, 1, 1. And if we wanted to test this, and that's not... that goes here. If we wanted to test this, then we can see that this will be 4 plus 2 plus 1, which is indeed 7. So that's how binary addition works. But what we have to ask ourselves is, what happens when we have a slightly more complicated problem? In particular, suppose we wanted to do the problem 0, 0, 1, 1, plus, or 3 plus 1, oh, how was I doing this? Yeah, like that. Plus 2. Right? Pretty simple problem, 3 plus 2, but it does raise an important point that we need to get to when we're doing binary addition. So, first of all, 1 plus 0, we can do that. That's 1. Easy. 1 plus 1. 1 plus 1 is 2. But in binary, there is no such thing as a 2, so what the heck do we do? Well, in binary, 2 is 1, 0. So what we end up doing is carrying the 1 in this case. So, we put a 0 down in this slot, and we carry a 1 up to here, like that. And there you go, now the rest is easy. 1 plus 0 is 1. So you can see that's given us the correct answer. 3, 1, 1, plus 2, 1, 0, is 5, 1, 0, 1. So that has given us the right answer, and you can convince yourself that this is the correct way to do binary addition. Alright, so that's as much as I want to do about the theory of binary addition. You can make up tons of binary addition problems for yourself if you aren't quite comfortable with this, but again, there's just one other problem that is important to try. This one. 9, 1, 0, 0, 1 plus 7, 0, 1, 1, 1. So that's 16, but how would we do it? Well, I'll just roughly walk you through it, and you can do the details by yourself. We'd start on this bit here, so we'd do 1 plus 1, we'd get a 0 here, and we'd carry the 1. Then we do another carrying, right? So we get a 1 plus 1, add another 0 there, carry the 1 to here. And guess what we do next? We do 1 plus 1, we get a 0 here, and carry the 1 to here. Then finally we do this 1 plus 1 here, and we put another 0, but this has nowhere to carry to. So just like in regular addition, you just put the extra 1 out on the other side. Now, this extra 1 actually has a name. It's called the carryout, but we'll see that in a moment. So you can check that this does indeed give us 1, 0, 0, 0, 0, which is 16 in binary. So now that we've done that, I think it's important to start actually building an adder. Alright, so the way we're going to figure out how to build this adder is to literally follow our thoughts through binary addition problems and see what we come up with. So, to start off with, when we're doing a binary addition problem, what do we check for first? Well, we want to add up this first digit, right? So, for instance, we can look at this problem. 1, 0, 1 plus 0, 1, 0. The first thing we do is we check if there's exactly 1, 1, 1, 1 out of these two bits here, right? There's a 1 here and a 0 here. So, because there's exactly 1, 1, 1 plus 0 is 1, and we get a 1. So, if we want to check that one of these is a 1, but not both, then what we do is we build an Xor Gate. So it's maybe a good idea to start building our adder cell by making an Xor Gate. So that's what we'll do. We'll come over here. Now, the most standard Xor Gate design is not too complicated. This is called rather disdainfully a wiki adder by many people in communities. Again, we're going to build an instacarry adder in the next video, hopefully, or maybe even in this one. So this is the Xor Gate we're going to use. So these will be the two inputs to our adder. So for instance, here we can do 1. If we have exactly 1 1 on, like before, then that will give us 1. So this is our 1 output. If we have this one on, it's the same thing, obviously. If we have both on, then this will be 0. That's the same thing as, say, putting a 0 down there. But you have to ask, where does the carried 1 go? Well, I included another torch here, this torch, which is on only if both of these torches are off, since that's what this redstone dust does. So this torch turns out to be our carried 1. If this is on, then that means we should carry a 1. So that's the first part. We have an Xor gate down here and an AND gate down here, and all together we call this thing a half adder. So that's pretty cool. Now a half adder, as we've built over there, is actually already ready to add one bit numbers. So if we forget about this part of the whole thing here, if this can add things like 1 plus 0, or 0 plus 1, or 1 plus 1, or 0 plus 0. It can do all 4 of those problems, but it can't do any of the other ones. So a problem that comes up is what happens when we, say, carry a 1 to this next bit. So suppose we've done that. Suppose we've carried a 1 to this bit. We've gotten a 0 here and carried a 1. Well, that's given by that top torch in our half adder. And now, if we were to just use another half adder, then the device would say, if we were to use a half adder for our next bit, then the device would say, well, I'm not even looking at this carried 1. I'm just going to say 0 plus 1, and that's 1. And that's wrong. That's clearly wrong. So we need a way to account for these carried 1s. Now, the way to do that, well, I'm just going to build it, and then we can see if we can figure out why it works, is going to be with another Xor gate. So we're going to come in here, and this is going to become one input to the Xor gate, to another Xor gate like this. This time, we don't need to build a full half adder, so I'm just going to put a torch down here instead. And then we're going to put 2 redstone dust here and here. Then 2 torches, and this will lead us to our output for that bit. So I'll just use a sticky piston as an output. Now, right now this does not account at all for the carry in. Now, what I'm going to do is I'm going to have the carry in, which is the carried 1 on top of this bit, be this other input to the Xor. So let's just do that and see what happens. We'll have to put a block here if we want to retain a piece of redstone dust here, like so. And this is our carry in. Now this can handle a bunch of different situations, so let's see. If we have only a carried 1, then let's see what happens. Well, we turn this on, we get a 1. That's just saying that 1, the carried 1, plus 0 is 1. So that's pretty simple. Now, suppose we had a regular input, so this is 1 now, and a carried 1. Well, that's 0, which is good. 1 plus 1 should be 0, but notice that this doesn't carry a 1 at all. To fix that, we can just stick a torch right here, and now that does that. It's exactly the same if we do, for instance, carried 1 plus 0 plus regular 1. That gives us 0 and a carry out. Finally, the one other case that's pretty important to try is to try it with all 3. So if we go 1, 2, 3, this is saying 1 plus 1 plus 1. Well, that's 3, which in binary is 1, 1. So that means that we get a 1 output here, like so, and we get a carry out. So this is carrying a 1 and giving out a 1, which is exactly what we want. Now, to make sure this works, we should try stacking this adder cell over a little bit. So that's what we'll do. You want to grab a block here, and let me just make sure I got that right. Yep, I did. And a block up here, like so. And stack it as many times as you want. I'll stack it 3 times, so we get a 4-bit adder. And there we go. That's that. Now notice that the carries chain together. So this is the output that carries the 1 to the next bit. This would carry another 1. So let's do a binary addition problem to see what happens. This switch, this switch, this switch, and this switch is one of our inputs. The other input is these other 4 switches here. So for instance, let's do that tricky problem over there. Let's do 1, 0, 0, 1. So that's just 9 right now. It goes right through. Plus 0, 1, 1, 1. So let's see what we get. Well, we get nothing, right? We got zeros for all those outputs. But here, we get the last carry out. We're carrying that 1 that has nowhere to go. So we can use this as the next bit and wire it over here. That's not right. like that. So indeed, this is 10000, 16. Alright, let's see what else we can do. Well, we can try another problem over there. 101 plus 010. 1, 0, 1 plus 0. Oops, that's the wrong one, isn't it? Yeah, 1, 0. No, that's right. Plus 0, 1, 0. When we do this, we do indeed get 111, which is 7. So as you can see, this works, and you can go through it yourself, do a bunch of other problems with it, try, for instance, 5 plus 8 and see if you get the right answer, and so on. So this is how binary adders work, and that's pretty cool. Alright, so we have binary addition. The next logical step would be to develop binary subtraction, and you might say, well, we've done all this for addition again, do we have to do it all over by going through our thought process for subtraction? Well, no. We don't, which is really, really good news. We can actually use this adder to do subtraction, after we use a little bit of a trick. So, the trick we're going to use is a very simple fact that I'll write down, although hopefully you know it. If we have any two numbers like this, A minus, and we subtract them, A minus B, we can write that in terms of addition, and of course I'm probably just reminding you of old stuff, but this is very important. We can rewrite this as A, again. Is that how I'm doing it? Yeah, that's right. Plus, oh, I'm gonna go off, that's fine. Plus, and then, in parentheses, yeah, it's fun. Oh, I'm gonna have to be anti-symmetric here, but okay, fine. Plus minus B, where this is the negative of B. Again, pretty simple fact from the most basic algebra, and I think I need a parenthesis at the end here. I'm not going to go through why that works because has nothing to do with Redstone computers, but there you go. A minus B is A plus minus B. So, to do subtraction, if we can figure out how to convert a number to a negative, if we can figure out how to start with the binary number B and get minus B, then we can just add it to A like before and be done. Now, you might say, how the heck do I do that? And the answer is a bit weird, so I'll show you. Well, let's start with some binary number. Let's start with the binary number, for instance, 1, 0, 1, and 0. This is the positive binary number 10. 8 plus 2 is 10. So this is our binary number, and we want to see how to find minus 10. Now there's a really strange way to do that, so there are two rules. One rule that converts a binary number from positive to negative. So to do that, what we say is we first invert the number. So we invert. So this goes to, if I can make a good arrow here, is that a good arrow? Is that a good arrow? Good enough arrow. So first of all, we invert. We change all of the numbers to their opposite. So we change all the zeros to ones, change all the ones to zeros, like this. So we end up with 1, 0, 1, 0, 1. Then we, I'm just gonna have to do that, I guess. That's ugly. But then we add 1 to this thing. So this is 5. 5 plus 1 is 6. And to do 6, we would do 0, 1, 1, 0. Now, as a positive binary number, this thing would be indeed 6. But now we're speaking of this as a negative binary number. So this thing is negative 10, as well as being 6. Now, normally what you'd do is you would include a sign bit. So, for instance, something would turn on, this 1, for instance, 1, 0, 1, 1, 0, And this sign bit wouldn't actually be used in the addition, it would just tell you that we have indeed turned this to a negative binary number. So that's just an important thing to keep in mind. So 0, 1, 1, 0 is negative 10 in binary. And that's just a rule that we'll be able to check when we use it to make a subtractor. Now, just to get more practice doing these calculations and to verify something important for this one number, if we start with the number 0, 1, 1, 0, you might ask, if we take the negative of this thing, do we get back to 10? We better, because negative times negative is a positive. But let's see if we do. Well, this goes to 1, 0. I'm not sure what the shadow's about. Hopefully you can still see. 0, 1. And then you add to that, and you get, indeed, 1, 0, 1, 0. So, that does work. The negative of a negative is a positive, at least for this one simple case. So, that's the 2's complement method of making numbers negative in binary. Pretty simple. So now we want to do this with our adder. Now that seems complicated, but it isn't. So first of all, we need the invert step. So, if this is our A input, then our B input will be these ones, so we can put torches there. And that just inverts all of the B inputs. That's all we have to do. All we have to do. Pretty simple. Couldn't be much easier. And then we have something like that, and we get some weird output. Now, how do we add 1? Well, that might be tricky, potentially, but it's not. We have something that's going to save us here, and that's the original carry-in. This isn't being used for anything in addition, since we're just carrying in, but what it actually does is serves to add 1 to this whole thing. So, if we just turn this on completely, then we'll see we'll get this. Now, you want to invert this, and now we have a subtractor. So let's try a problem. Let's do 5, so that's 1, 0, 1. No, yeah, 1, 0, 1, which is, so 5 minus 0 is indeed 5, minus 3, minus 1, 1. So what we should see is only this bit being on, because that represents 2. And indeed it does. So this is being very good in verifying that 2's complement, which is what this inverting and adding 1 stuff is called, actually is the negation of a binary number. We can try another problem. For instance, we can try 10, which is 1, oops, that's minus 10. 10, 1, 0, 1, 0, minus 7. That should be 3. And hey, look, it is. So we see this working very well. And you might ask, well, what happens? What happens when we, oops, that shouldn't be there. What happens when we try to get a negative answer? So when you do subtraction, you can get a negative answer. For instance, we can do the problem 2 minus 6. So 2 would be here. Minus 6 would be this and this. And then we get this odd-looking thing. Now notice that our carryout is now on. Technically it's off, but we inverted it, so it turns on. I claim that this thing is our sign bit. So this is the output sign. If this is on, it's negative. If it's off, it's positive. So this is telling us we have a negative number, and right now we have 1, 1, 0, 0. So the answer to 2 minus 6 should be negative 4. So if we convert 6 to negative, or if we convert this negative 6 to a positive, we should get positive 4. Let's see if that works. So if we start with 1, 1, 0, 0, we invert that and get 0, 0, 1, 1. If we add 1 to that, then we'll get 1, 0, 1, 0, 0, and you can verify all this yourself, and indeed that is positive 4. So, what this shows is that this binary subtractor actually does work as a subtraction device. Now, if you have any questions about this is a bit abstract, but what you really need to do is just play around with this stuff, addition and subtraction, for a little bit until it makes a bit more sense to you. If you have any questions, feel free to leave them in the comments, and yeah, Hopefully you enjoyed this episode. Next time we'll be making an instant carry adder, which I'll explain a bit more. And yeah, and as always, well, bye now.